So just a quick primer on polynomial functions. So a polynomial, if you recall, is an expression of the form a sub n x to the n plus a sub n minus 1 x to the n minus 1 dot 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 till we get to a to the 0. So an example of that would be like 3x cubed, where this is a coefficient, minus 7x squared plus 2x minus 5. Then this would be the, a times x to the 0. A sub 0 times x to the 0. Because 5 times x to the 0 is just equal to 5. So that's that. X to the 0 is one term. So notice how we have descending order of exponents on our terms. That's how we in the standard way set this up. It's convention. You could write the definition a whole bunch of different ways, but that's generally what we're talking about. So when we're talking about polynomial functions, we're talking about polynomials used as functions on the Cartesian coordinate system for one particular situation or case. So if I have a coordinate plane or coordinate axes, and I plot, for instance, the function where this exponent is 1, I'll get some 3x plus 5 or something to that effect. And so I have, 1, 2, 3, 4, 5, and a slope of 3. And so I get something that looks like this. Something that looks like that. So that's a polynomial function of degree 1. Polynomial function of degree 2 would be your quadratic function. And let's just go with x squared, the parent function. And so that one looks like this, or something like it. It's not drawn to scale, and the points aren't quite right, probably. And then as we go up here, we have a cubic. The parent function is f of x equals x cubed, or y equals x cubed, and it looks something like this. Okay, and so let's do a little bit of a summary on polynomial functions. If I have y equals x, I'm going to get a line. And so y equals x equals x cubed, y equals x to the 5th, and so on. And so what we get as our graphs, we get y equals x looks something like that. Y equals x cubed looks something like this. Y equals x to the 5th looks like something like this. Looks skinnier than y equals x cubed. Y equals x squared looks like this. Y equals x to the 4th looks like this. It's a little bit flatter on the bottom. Y equals x to the 6th looks like this. It's a little bit flatter on the bottom. What ends up happening is all of your even exponents open on the same side. It should make some sense, because if I have put an x value in that is negative, like -1, if I put -1 in here for x, I'll get 1. I'll get a positive value. If I put a negative number in for that one, it'll become a positive value. If I put a negative number in for this x, it'll become a positive value. So all of these have no negative values coming out of them unless we transform them. So understand, unless we transform. So I'm talking about the parent functions that are in front of you right now. With the functions with odd exponents, I can get negatives, so I get these negative values and these positive values. Very much like a line, except it becomes curvy and curvier still as we get x to the 5th. In fact, as we transform these, for instance, I can get graphs that have, quote, bumps, or more mathematically stated, local minimums and local maximums. And we'll give you 2 examples here, and then we'll wrap it up. So let's say I have y equals x to the 5th plus 3x squared minus 7. I have no idea what that looks like, but it could have as many as this many like turns or changes in direction. So it could have 1, 2, 3, 4 changes in direction. Changes in direction of n minus 1. So 4 changes in direction. Whereas if I had y equals x to the 4th plus 2x squared minus 5, something like that, this one has an even, so I know it starts in the same direction, but it can have 1, 2, 3 changes in direction. Again, n minus 1 changes in direction. Okay? So that's some basic information about polynomial functions. We'll get to more information extending past the parent functions when we start talking about transformations. All right, that's it.